guys, and welcome to part 2 of our review for our acids and base test. So we're going to pick up where we left off from part 1, which is actually strong and weak acids. So let's take a look up here at letter A from the first part, and actually this question reads, I guess I should put this here. So this is where we were yesterday. Fill in the following blanks with the terms strong acid, strong base, or weak base. So now we have A through F that we're going to do that for. Look at A. A contains 100% electrolytes. If it contains 100% electrolytes, that means there was 100% dissociation, which means you had 100% ions. Well, that means it's a strong something. Well, let's see. Do we have another clue? pH of 9.4. Well, what's a pH of 9.4? That would be a base. So this is going to be a strong base. In B, dimly lights up a conductivity apparatus. Well, if it's dimly, that means we have less than 100% dissociation, less than 100% ions, so it's got to be a weak something. So it's going to be weak, so let's find out what our other clue is. It dissociates into hydronium. Well, remember, hydronium is H3O positive. That's an acid. Remember, an areneous acid. So this would be a weak acid. C, it dissociates partially. Well, if it dissociates partially, we're back to this one. Less than 100% dissociation, which means it's less than 100% ionization, and it would light this thing up dimly, so it's going to be a weak something. And let's see, what do we have? It dissociates partially into hydroxide. Well, what has hydroxide? Bases, so this would be a weak base. Let's look at part D. Contains a few electrolytes. Well, we're back to few, so that means we've dissociated less than 100%. We have less than 100% ions, so it turns pink in phenolphthalein. So there's our other clue. Well, what is it that turns pink in phenolphthalein? If you look back a page or so, you'll see that phenolphthalein turns pink in a base. So this is going to also be a weak base. Look at E. It brightly lights up a conductivity apparatus. Brightly lights up. Well, if it brightly lights up this conductivity apparatus, that means we're at 100% dissociation, which is 100% ions, 100% electrolytes. So it's going to be a strong something. So that's what another clue is. Turns purple on pH paper. Well, what turns pH paper purple? Well, if we take a look at pH paper, you have red, orange, yellow on the acid side, green in the middle. You know what? I'm just going to put that here. Active 7, 0, 14, acid, base. Alright, so it turns purple. Well, down here in this area, this would be the green, blue, indigo, violet, red, orange, yellow on pH paper and universal indicator. So violet is purple, so this is going to be a strong base. Dissociates 100%. Well, now we're back up here with this, so it's a strong something, stays clear in phenolphthalein and turns blue litmus paper red. Well, clear in phenolphthalein, that could either be neutral or an acid. So let's look over here. Blue litmus paper to red. Well, if it's red, acid. So this would be a strong acid. All right. Look at 18. Acid A and B are tested with a conductivity apparatus. When the conductivity apparatus is placed in acid A, the light glows dimly. When it's placed in B, the bulb glows more brightly. Which acid is stronger, and how do you know? Okay, so A is dim, and B is bright. Well, let's put that together with what we just did up here. If it's dim, that means that you have less than 100% electrolyte, less than 100% ionization, so it's got to be a weak something. Well, it said it's an acid, acid A, acid B, so it's a weak acid. And we know that because of the fact that this is dim. It had to have been less than 100% electrolytes and less than 100% ionization, because it's less than 100% dissociation. In other words, it doesn't come apart 100%. B is very bright, so that means you've got to have 100% electrolytes in order to make that bright. That means you, in order to have 100% electrolyte, you must have had 100% ionization. In order for it to be 100% isolation, you had to have had 100% dissociation. So B must be a strong acid. So B is stronger than A because of the fact that only 100% electrolytes would light it brighter than the other. 100% dissociation is what's going to cause 100% ionization, which gives you 100% electrolytes, which gives you this bright light. All right, so let's take a look at acid nomenclature and formula writing. All acids contain what element? And this is something that I see often when people are naming acids or writing the formula for an acid, especially an acid that doesn't have hydrogen in the name. They forget that hydrogen atoms are found in every acid. Acids contain hydrogen ions. So, how can you differentiate between a binary acid and an oxyacid when looking at the acid name? Well, if I'm looking at the acid name, if it is a binary acid, that means one that does not have oxygen in it. The first part of its name will always be hydrochloric acid, hydrosulfuric acid, hydroiodic acid, hydrobromic acid. If it is an oxyacid, however, so for oxyacids, I know that it is not starting with the word hydro. So no hydro. No hydro if it is an oxyacid. If it starts with the word hydro, it's a binary acid. If it starts with a word of whatever that ion is, the anion, then it's an oxyacid. If we're looking at the formula, well, if it's a binary acid and we're looking at the formula, we're going to see two elements only and no oxygen. And if it is an oxyacid, we will see multiple types of elements, usually those polyatomic ions that are on the back, and oxygen is present. Oxygen is present. So let's try these. HNO2. HNO2, NO2, that contains oxygen, which means that it is an oxyacid, which means that I'm not going to put the word hydro in front of this acid. Okay, so I see an oxygen here, so I'm just going to come on over here and write oxyacid, because I know that. Well, what is NO2? NO2 is nitrite. Well, let's think, what is our rule? Ate, ick, ite, us. Atikitis. Nitrite becomes nitrous. So this would be nitrous acid. All right, let's look at the next one. Hydrosulfuric acid. Well, I see hydro, so this is going to be a binary acid. I know that in its formula, it's always going to have an H because that starts every acid. Sulfuric. What element could that be? Oh, could it be sulfur? Well, I can't just leave it like this. Sulfur has an oxidation of -2, so that would be H2S. All right, look at the next one. HClO3. ClO3, I see this oxygen right here, so that tells me straight away I can come down here and write oxyacid. So now I just need to look on my periodic table and find out what ClO3 is. And it turns out that ClO3 is chlorate, 8-ic. So this becomes chloric acid. Don't forget, there is a whole video on my e-class page that goes through all of this naming. Okay, look at D, HI. Well, 1, 2. Got 2 elements, no oxygen, binary acid. Since it's a binary acid, I know I've got to start it with the word hydro. So, look at the next element, I, iodine, so hydroiodic acid. All right, sulfuric acid. Sulfuric acid. Well, it doesn't start with hydro, so that means it's got to be an oxyacid. So now I need it's sulfuric. So I'm going to look for what became ic? 8. Sulfate. So I need to look for sulfate. Well, sulfate is SO4 and it has a -2 charge. So H2SO4. Sulfurous acid. Sulfurous acid, I don't see the word hydro here. So this has got to be an oxyacid. Sulfurous. Us-ite. So this is actually sulfite. So I look on my periodic table and find sulfite, which is SO3. SO3 also has a -2 charge, which means that I've got to have 2 hydrogens to balance that out. So there you go. Again, don't forget, there's a whole video on my e-class page all about naming acids. It was from last week, the week before we got out for spring break. All right, acid-base reactions. These are our neutralization reactions. And remember, a neutralization reaction does not necessarily end with a pH of 7. All right, so Let's fill in the blanks. When an acid reacts with a base, a blank reaction, a type of blank reaction, takes place. So this is a neutralization reaction. Remember, in a neutralization reaction, you've got two compounds in the product as well as the reactants. So this is a double displacement or double replacement. So a double displacement reaction takes place. This means blank and blank are produced. Well, in a neutralization reaction, water and a salt. Now, I don't necessarily mean table salt, although sodium chloride can be produced if the right two things react, but water and a salt are produced. Explain how a salt is formed during a neutralization reaction. Be specific. Well, you know that if water takes the hydrogen from the acid and the hydroxide from the base, this is going to leave the anion from the acid and the cation from the base. So in this double displacement, the hydrogen from the acid, the OH from the hydroxide from the base, they come together, making water. And in the other product, the cation from the base and the anion from the acid come together and make your salt. So that would be your salt. So this last page is all about writing equations and, of course, balancing those equations. Let's see if we can get these. All right. This is going to cause some issues, I can tell, when we're trying to write these out. Sodium hydroxide. Well, let's see. Sodium and hydroxide. Sodium hydroxide. Sodium is +1, hydroxide is -1, so there's my formula for sodium hydroxide. This is going to react with chlorous acid. We've got to write the formula for chlorous acid. Well, I think we just had that on the other page. Chlorous acid, this is chlorous, that means it's got to be chlorite. So chlorite is ClO2, and I know I've got to have a hydrogen in there. And hydrogen has a +1, chlorite has a -1, so that simply cancels out. So there's HClO2. So there's our chlorous acid. So what is this going to produce? Well, I know that my hydrogen here is going to come together with the OH here to make water. Now, I'm just going to write it as HOH. I usually do this whenever I'm writing neutralization reactions so that you can follow. The OH is here, the AH is here. Plus, now let's take a look at our other product. The sodium from the sodium hydroxide and the chlorite from the chlorous acid. So that's going to be sodium chlorite. Sodium is +1, chlorite is -1, so after your crisscross, then there you go. Now, if we have done everything right, actually this should be balanced already. 1 sodium, 1 sodium. 1 OH, 1 OH, 1 H, 1 H, 1 chlorite, 1 chloride. So yeah, we're all good. All right, so there you go. Look at the next one. Hydrosulfuric acid. Hydrosulfuric. Well, hydrosulfuric means it's a binary acid, so H H2S. No, I can't leave it that way because sulfur has a -2 oxidation. So when I bring that down here, we have H2S plus potassium hydroxide. Potassium hydroxide. Potassium is +1, hydroxide is -1, so that's all good. Yields. Now let's see what it yields. Well, first of all, yet again, my hydrogen from the acid and the hydroxide from the potassium hydroxide is going to make my water plus my cation from the base and my anion from the acid. Potassium sulfide. There's a 2 here because sulfur has a -2 oxidation, potassium has a +1, so when you do your crisscross you get this formula. That's last semester, shouldn't have to worry about that. Now, this is definitely not in balance, so let's see what we need to do. If I look, I've got 1 potassium here, 2 potassiums over here, so that's going to tell me straight away that I should probably put a 2 in front of that. So now that's going to give me 2 potassiums and 2 hydroxides. Well, if I've got 2 hydroxides, I've only got 1 hydroxide over here. So if I put a 2 here, now I've got 2 hydroxides, and so that matches. So let's see, 2 hydrogens. Well, I've got 2 hydrogens over here, 1 sulfur here, 1 sulfur here, so we were balanced. Phosphoric acid and calcium hydroxide. So phosphoric, well, it's not going to be a binary acid, so I've got to look for phosphoric. What became ic? 8. So I've got to look for phosphate on my periodic table, which is PO4. Well, PO4 has a -3, and it's my acid. So -3, I'm going to bring right down to here. Notice I'm not even putting anything over the hydrogen. Think about what goes over here because hydrogen is just +1. So regardless, whatever this charge is, I simply bring it down over here and put that. Plus calcium hydroxide. Well, I can't leave that like that because hydroxide is -1, calcium is +2, so there. So, what will this produce? Well, we know we're going to have water, so taking the hydrogen here and the OHs here, I know that I'm going to produce water. Then my calcium and my phosphates I'm going to use my pencil and I'm going to put in the charges for this one because some of us might not remember exactly what was going on here. So I've got +2 for calcium. Phosphate has a -3. So when I do my crisscross, 3 goes here, 2 goes here, which means that I've got to have my parentheses. Now let's take a look at our balance. I have 3 hydrogens here. I could put a 3 here, but let's hold off on that for a second and let's take care of this other thing. I've got 3 calciums here and I've got 1 calcium here. So if I put a 3 here, in order to balance my calcium, that's also going to give me three hydroxides. Actually, it's going to give me 6 hydroxides, right? Because I've got 2 already here and 3 sets of these 2. So that's a total of 6 hydroxides. Well, if I have 6 hydroxides, I'm going to have 6 waters going on over here. Well, I've only got 3 hydrogens on this side, so if I put a 2 right here, now I should have 6 hydrogens, 2 phosphates, 6 hydrogens, 2 phosphates. I'm going to erase these charges. 3 calciums, 3 calciums, 6 hydroxides, 6 hydroxides. So there you go, that's balanced. All right, 3 more. Let's see if we can do these really quick. Calcium hydroxide plus sulfurous acid. Well, if it's sulfurous, then that would have been sulfite. So I've got to have sulfite, which is SO3. There's my H. Well, sulfite has a -2 charge, so I put a 2 here. So there's my acid and my base. Hydroxide and hydrogen. And so there's my water. Calcium sulfite. So calcium and then SO3. Well, calcium sulfite, that makes it pretty easy because calcium is +2, sulfite is -2, so we're good to go. Well, let's see if we're in balance. If I look, I've got 1 calcium and 1 calcium, so that's good. 2 hydroxides, 1 hydroxide. So let's put a 2 here. So now I've got 2 hydroxides. 2 hydrogens, 1 sulfite, 1 sulfite. So I'm all good. Next one, lithium hydroxide plus, now let's take a look at that. Take a look at my periodic table and see if we need to change anything. Lithium is a +1, hydroxide is a -1, so that cancels out, so that's all good. Dichromic acid. Well, dichromic would have been dichromate, so I need to look on my periodic table and find dichromate. Well, dichromate is Cr2O7, and that has a -2 charge, so it's H2Cr2O7. That's going to yield, well, let's see what we've got. I've got hydrogen and I've got my OH. So HOH, there's my water, plus lithium dichromate. Well, lithium is a +1 and dichromate is a -2, so that's got to be a 2. So let's see if we're in balance. I have 1 lithium here and 2 lithium over here, so I've got to have 2 lithiums. Well, that gives me 2 OHs. Well, I only have 1 OH over here, so I'm going to put a 2 here. So that now gives me 2 hydrogens, 1 dichromate, 1 dichromate, so we're all good with that balance. And the last one, phosphorus acid. Well, if it's phosphorus acid, that means it must have been phosphite. Remember, ate, ate us. Or ate, us. So it had to be, to become us, it had to have been phosphite. Well, phosphite is PO3. Phosphite, if I look on the back of my periodic table, I see phosphite has a -3 charge, so I've got to have H3 for my acid plus aluminum hydroxide. Aluminum and then hydroxide. Well, aluminum is +3, hydroxide is -1, so that means I've got to have 3 of those. Well, what do we end up with? Again, there's my H and my OH to make my water. Aluminum, because that's my cation, and phosphite. Well, let's take a look at aluminum phosphite. Aluminum has a +3 charge, phosphite has a -3 charge. So when this comes here, and it goes away, so I don't have to deal with that. So now all we have to do is balance it. I have 3 hydrogens here. Well, if I take a look just real quick, that means I've also got 3 hydroxides. So that's going to make 3 waters. So I can just go ahead and put that there and take care of that. 1 phosphite, 1 phosphite, 1 aluminum, 1 aluminum. And there we go, that's balanced. And that's it. So that's writing the equations, and that was actually a nice practice in making sure that we knew names, making sure that we knew how to write formulas, and using our periodic table to make sure that we have the right oxidation numbers to write those formulas. Every acid-base reaction, every neutralization reaction is going to produce water and a salt. So there we go. So again, all the way up. And that concludes all of our work for this review packet. So with that, good luck everybody for your test, and don't forget to, if you have any questions, you can send a remind text or an email, and I'll get right to it. Thanks a bunch. Have a good afternoon.